Okay, let's get started. Today we are going to study some general methods that can be, not that can be, that are very useful when it comes to studying, examining the solutions to dynamic optimization problems. Let's start with the basics as a kind reminder. In the past few lectures, we learned that any dynamic optimization problem can be written as in a sequential form, which has a related Bellman equation or functional equation. Our textbook uses the functional equation label. So such a dynamic optimization problem can be studied and solved through solving the Bellman equation. What is a solution to such a Bellman equation, to such a dynamic optimization problem? Actually, our foremost interest is in the policy function, because this is the equation. The policy function is the function that describes the dynamics of the state variable, the endogenous state variable. But such a policy function comes together with the value function. So if we find the value function, we under strict conditions, under some strict conditions, we are going to find the policy function. So once again, first of all, we want to find the optimal policy function, but to find this policy function, we need to find the value function. So unfortunately, we are unable to find a policy function without a value function. So these two solutions, the value function and the policy function, come together. And to have them, we need to solve the Bellman equation. Uh, in chapter 4 of the book, we studied some very strict assumptions that must hold in order that we have an appropriate solution to the problem. So assumptions 4.3, 4.5, 4.7, 8, and 9. If these assumptions hold, we have a unique bounded, strictly increasing, strictly concave, and continuous value function for the Bellman equation. So this value function solves the Bellman equation, and under these conditions, under these assumptions, this value function is unique. As I have just mentioned, we also have a single valued policy function that satisfies the Bellman equation. So here you can see that the Bellman equations, the value function that satisfies the Bellman equation and the policy function they come together. So uh, if we formalize the dynamic optimization problem in the appropriate form, by which I mean that we formalize the problem in a form in which all the necessary assumptions hold, we have an appropriate solution. So this is the point where we start today. Uh, let's assume that we have an optimal solution to a very general dynamic optimization problem. Such a solution means that we have a sequence of the endogenous state variable, so we can describe the dynamics of the endogenous state variable. Such an optimal solution can be characterized by 4 equations, and this is very important because this is the starting point for us today. So we have 4 equations that equally and mutually describe, together they describe the optimal solution. So an optimal solution, in other words, an optimal solution must satisfy all these 4 equations. These equations are the first order condition, which we receive by derivating the Bellman equation with respect to the decision variable y. We have the envelope condition, which we receive by derivating the optimal value function with respect to x under the assumption that we have the optimal policy function. And according to the envelope condition, if we want to understand the effect of the change of any change of the endogenous state variable, all we need to do is to derivate the value function with respect to x by neglecting the indirect effects that come through the policy function. The third crucial equation is the Euler equation, which is, you can see, is a second order difference equation. So for today, this Euler equation is of central importance for us, because even if we don't know, you will see that even if we don't know the policy function, there is one thing we know for sure, that if we have the optimal policy function of whatever form, we don't need to know exactly in a closed form the policy function satisfies the Euler equation. So the Euler equation can be used to learn more about what dynamics the policy function determines and the transversality condition. So these are the four conditions, these are the four equations that hold under any optimal solution to any dynamic optimization problem. We have some problems that we need to solve today, and we are going to solve these problems today. First, we want to know whether there is a unique steady state, and if there is one, so there is a unique, if there is a unique steady state, a stationary point, we want to know if it is locally and globally stable. We will make the distinction very soon. This is the first problem. So in a nutshell, we want to know if there is a steady state, a unique steady state, where the system is stable. And a second related problem, the system may be, what we analyze may be so complex, plus we don't have the policy function and the value function in closed forms. You may remember that in the first lecture we worked out a complete solution to the cake eating problem. It is a very simple problem, the simplest possible actually. And in such a case, in that case, we had a closed form solution to the value function and a closed form solution to the policy function. This is the exception, not the rule. So normally in our problems we are not going to have closed form solutions for either the value function or the policy function, but still we want to know something about the dynamics, the most possible about the dynamics that the policy function determines. It is a strange situation because we know, if you have a look at the assumptions, you will easily realize that under the crucial assumptions listed above, under these assumptions, we can know for sure that there is a policy function, a unique policy function, but we are unable to have a closed form solution to the policy function. So we know that there is a policy function, but we cannot write it down. So our best bet is to describe as closely as possible the policy function which we know exists. So this is what we are going to do. We are going to do today. So we will try to study in a simplified form the dynamics that the unknown policy function determines. Okay, let's jump right in. So what we want to do is to characterize, describe as closely as possible the solution to a dynamic optimization problem. In the heart of the problem, there is a policy function that describes the dynamics of the state variable. Normally, we don't know the closed form of such a policy function. Um, the best bet is to make sure that such a policy function exists. So we need to formalize the problem in the form in which the crucial assumptions listed above hold. But we know that such a policy function exists, and we want to characterize the dynamics that the policy function determines. But I cannot emphasize too much that the heart of the solution is the policy function, but we don't know the policy function. So we need to find an indirect way in which we can have a firm knowledge of the dynamics of the problem. Such a policy function is normally nonlinear. A policy function is a difference equation because on the basis of the state at t, the policy function determines the state variable for the next period. So formally, at a very abstract level, such a policy function is a first-order difference equation. But this difference equation is nonlinear generally. We have problems in which we can have linear difference equations. When the one-period return function is quadratic, in such problems the policy function is linear, but let me warn you that generally we cannot expect the policy functions to be linear. So what we know is that we don't have the closed form solution of the policy function, and we know that the policy function as a first order difference equation is non-linear. So what we can do now is to find a linear approximation which is linear to the dynamics that is determined by such a policy function. As I have just mentioned, a policy function, an optimal policy function, must satisfy the Euler equation. So the Euler equation can be a starting point because even if we don't know the policy function which we know exists satisfies the Euler equation. So the Euler equation can be used to find, and this is what we are going to do today, it can be used to find the steady state, the stationary point of the problem to which the state variable tends, or towards which the state variable tends. So through the Euler equation we can find the steady state, and this is the main idea, and this is what we are going to do today. Even if the policy function is nonlinear, so the dynamics of the problem is nonlinear altogether, in the very close neighborhood of the stationary point, a linear approximation to the original nonlinear dynamics may work well. So instead of trying to solve the impossible, by which I mean instead of trying to find a closed form solution to the policy function, we can try to find an indirect way to describe, to characterize the solution through linear approximations. So what we are going to do is to set up linear approximations to the Euler equations through Taylor polynomials, and we will find the steady state, and in the very close neighborhood of the steady state we will set up a linear approximation to the dynamics, to the nonlinear dynamics, and if in the very close neighborhood of the steady state the steady state proves to be stable, then we can say that that the steady state of the original nonlinear dynamics is also stable. But please let me aware you that such linear approximations or approximations, so such a linear approximation cannot be used to describe in a simplified form the whole dynamics of the problem. So if we have a problem in which we have a nonlinear policy function, even if we can set up a linear approximation to the dynamics, this linear approximation will be disappointing, would be disappointing if you wanted to use a linear dynamics to describe, to approximate the nonlinear dynamics altogether. So such a linear approximation is useful only in the very close neighborhood of the steady state, of the stationary point. So after this short introduction to the slide, let's turn to the question of local stability before turning to global stability, which we are going to solve in the end of the day. So to judge the local stability of a nonlinear dynamics, we will study the local stability of a linearized linear system. So this is the reason why we need the theory of linear difference equations. I'm sure you are familiar with the theory of linear difference equations. If you are not, the textbook, the Stokely-Lucas book, gives a pretty accurate and very brief and effective summary of the theory we need. If you need more, the Sitzsater-Hammond handbook I recommended in the first lecture is another useful source. So what we need now is to state that we can find the steady state of a linear difference equation very easily, and this is the first thing we need. And the other thing we need is that it is very easy to switch to difference variables by subtracting the two difference equations. You can do the math on a sheet of paper in a minute, so it's very simple. So we can switch to the use of difference variables because by the use of such difference variables we can get rid of one of the parameters, a0, in the difference equation, and the second reason is more important when it comes to setting up the linear approximation to the Euler equation through the Taylor polynomials. The Taylor polynomials use such difference variables, so this is very useful. So the stability of such a linear system depends on the eigenvalues or the roots of the characteristic equation of the matrix. Both expressions are equally good and accurate. So the stability of such a first order difference equation depends on the eigenvalues of the matrix A. So we have two results, Theorem 6.3 and 6.4. 6.3 is the simpler because according to this theorem, if the eigenvalues of matrix A is strictly less than 1 in absolute value, then any sequence that satisfies the difference equation tends to the steady state, to the stationary point of the equation. This is very useful. Unfortunately, this is the exception, not the rule, but this is a fortunate case because practically it means that starting from any x0, we cannot but find the steady state in the end. Problematically, we cannot expect all the eigenvalues to be less than 1 in absolute value, so practically, as you will see it in the textbook, practically some of the eigenvalues are appropriate, so they are below 1 in absolute value, but some of them are higher than 1. In this case, and this is the main message of Theorem 6.4, it is possible to find starting values. It is possible to find sequences along which we can get to the stationary point, and it means it is possible to find the stable manifold of the problem. So the difference between Theorem 6.3 and 6.4 is that under Theorem 6.3 any sequence any sequence leads to the steady state, and under Theorem 6.4 only a subset of the possible sequences leads to the steady state. And our task, and this is what we are going to do in the next couple of minutes, our next problem is to find the way of finding such sequences that lead to the stationary point. Okay, let's have a look at Theorem 6.4 in action, because I like to show you what it means to find appropriate starting values for the process xt. So we need to find appropriate starting value x0, and we will see what it means. In this general setting, the state variable is an n-dimension vector. We know from the previous studies that the dynamics of the difference variable can be described with a very simple first order difference equation, which I expand to be as clear as possible. And this is also true. I am just rewriting the same equation, but here comes the fun part, because here this is the well-known Jordan decomposition of the matrix A. And following Stokes and Lucas, let's introduce a new label for this part of the equation. This is WT. Given that, okay, first, what it means to have a Jordan decomposition of matrix A. Lambda is the diagonal matrix of the eigenvalues of A. B is the matrix of the related eigenvectors, and B minus 1 is the inverse of matrix B. Under Theorem 6.4, we have a problem because matrix A has eigenvalues which are not equal to, which are not less than 1 in absolute value. So some of the eigenvalues of A are equal to or higher than 1 in absolute value. So this dynamics can be written in this form, and it is obvious that xt tends to the stationary point if and only if wt starts to 0. What is wt? Again, this is wt, and from this it follows that W0 is this. Or, in a simpler form, this is W0. All right. We are interested in this process, which is the same as this process. And this is interesting because the convergence, once again, the convergence of xt depends on the convergence of wt. And you know, if wt converges to 0 depends on lambda, matrix lambda, which is a diagonal matrix, and we have the eigenvalues of A along the main diagonal. So lambda is an n times m matrix. We have n distinct eigenvalues, and we assume that the first m, this is ugly, the first m eigenvalues are strictly less than 1 in absolute value, but there are n minus m pieces of eigenvalues which are equal to or higher than, larger than 1 in absolute value. You know, in power, the appropriate eigenvalues tends to 0. They tend to 0, but under the line, so this is n, this is m, under the line, so in the problematic region of the last n minus m eigenvalues, these eigenvalues tend to infinity. So wt is going to tend to 0 only if W0 is appropriate. It means that Wt tends to 0 only if the last n minus m dimension of W0 is 0. It is clear, I guess, so some of the eigenvalues disappear in power, but on those eigenvalues which are not going to disappear in power, there the elements of W0 must be 0. So, what is this vector W0 is exactly? This is W0. Let me expand this equation. And this is what we have. By solving the equation. So let me draw the figure. So this is W0 with the problematic dimensions. This is B, the same n times n dimension. And this is the the vector that contains the starting value for the process xt. And this is the requirement which we need to hold when it comes to finding appropriate starting values for the process xt, because in the last n minus m dimensions must be 0 in the last n minus m dimensions. The matrix W0 must be 0. So we need to find starting values for x1 by this equation. So this is what Theorem 6.4 tells us. When the eigenvalues of matrix A are not all appropriate. So if some of the eigenvalues of matrix A are equal to or higher than 1 in absolute value, then x0, the starting value, the starting vector of the process must be so that this equality holds. When it comes to solving concrete problems, it is easy to solve this equation. Actually, it's a system of linear equations in which some of the values are 0, so we need to find appropriate values, the values for x0 when the related dimensions, when in the related dimensions wz is 0. That's all. It's very simple. Okay, let's go ahead. We have just seen why the eigenvalues of the parameter matrix of a vector linear difference equation is so important, and we are going to use this knowledge in the linearization of the Euler equation. So what we are going to do now, we want to describe as closely as possible the dynamics that a policy function we don't actually know determines, and in these attempts, linearization is a way out. So we want to work out a linear equation instead of the nonlinear dynamics in exchange for the nonlinear dynamics, and we want to study in the close neighborhood of the stationary point the behavior of this linearized difference equation. So we know that we have a single valued optimal policy function, and we know that this single valued policy function satisfies the Euler equation. The Euler equation is a second order difference equation, and it is a sum. So the idea is very simple. Let's try to find linear approximations to both components in this sum. In these linear approximations, we use Taylor polynomials. You should be familiar with the basic theory of Taylor polynomials. They are effectively summarized in the Sitzetter-Hammond handbook. So please, if you are uncertain about the theory of Taylor polynomials, please go back to the Sitzetter-Hammond book and refresh your command in this part of real analysis. So we set up the simple Taylor polynomials to the components of the sum in the Euler equation, and after some manipulation we have a simple matrix or vector difference equation, and this is the point where I want to highlight that it is possible to stack any higher order difference equation into a first order difference equation. You can see that it is a second order. In the difference variable, it is a second order difference equation. Zt plus t plus 2, t plus 1, and zt. This is a second order difference equation. But by appropriately wrapping up these variables, we can reduce the whole stuff into a first order difference equation in which we have a parameter matrix. And this is the parameter matrix of central importance. So referring back to the previous slide, this is the parameter matrix we labeled as A previously. So we have a first order linear difference equation with a parameter matrix, and the stability of this linearized process is dependent on the eigenvalues of A. So this is the part where the pieces come together. By the use of Taylor polynomials, we set up a linear approximation to the Euler equation, even if the policy function is nonlinear. But we know that in the very close neighborhood, because we know that in the very close neighborhood of the stationary point, this linear approximation will work quite accurately. So we are interested in, I'm just summing up, we are interested in setting up a linear approximation to a nonlinear dynamics, because in the close neighborhood of the stationary point, the stability of the original dynamics can be quite accurately described by this linear difference equation. So all we need to do is to have a linear difference equation and to describe, characterize its eigenvalues. If both eigenvalues are less than 1 in absolute value, we can say that the stationary point is locally stable for any starting value. Unfortunately, this is the exception, not the rule. So some of the eigenvalues may be larger than 1, equal to or larger than 1 in absolute value. The textbook shows some generally applicable methods to prove that one of the eigenvalues is less than 1, or some of the eigenvalues are less than 1 in absolute value. For instance, there is one thing I want to highlight. These eigenvalues usually come in reciprocal pairs, and it is easy to, and if it is the case, it is very easy to show that if one of the eigenvalues are higher than 1 in absolute value, the other is going to be less than 1 in absolute value. Unfortunately, there are not too many general rules, so some intuition and some creativity is definitely needed when it comes to solving and working with a linear system. And in the next couple of minutes we are going to do this. So I'm trying to show you a problem which is going to be solved in a linear form. This is what we are going to do now. Okay, let's have an exercise to see what it takes what it takes to set up a linear approximation to an Euler equation. This is a very simple model. This is a consumption model in which the utility of consumption is measured with this utility function in which alpha falls between 0 and 1, and we have a production function because the consumer is supposed to produce two goods, one consumption good and one capital good, and the production of the consumption good takes both labor force and capital, while the production of capital takes labor force only. So this is how consumption, this is N, this is how consumption good is produced. So it takes the labor force and a production function, while capital for next period is produced by labor force only, where of course labor force lies between 0 and 1. From this equation we can simplify. It's gonna be very useful soon, and from this part of the problem it follows that the control lies between 0 and 1, so the state also lies between 0 and 1. So this is the basics of the problem. Using these facts, we get to this form. This is equivalent to the previous formulation, but under the concrete, the given functional forms. And if we put consumption into the utility function, we will receive this equation, from which it is easy to describe the one period return function in the simplest form possible. Okay, so we are going to use this form as the one period return function. From the one period return function, it takes only one step to get to the Bellman equation or functional equation here with the correspondence we use that we know that the optimum choice for next period capital stock lies between 0 and 1. Yep. So this is the Bellman equation. All right. The first, all the time, every time when we solve such a problem, the first thing to do is to check if the basic assumptions hold. I did this, and please trust me, they do. So everything is given, and we can know for sure that the problem is formalized in a way which leads to a unique and appropriate solution. There is one point in this phase that deserves special attention, and this is the check of assumption 4.7 regarding the strict concavity of the one period return function, not in itself, but because the strict concavity must be demonstrated by the use of the Hessian, the Hesse matrix, the determinant of the Hessian, and to this end we need the partial first and second derivatives. We are not going to prove the strict concavity of the one period return function. I did this and it is strictly concave, but we are going to use these partial derivatives in the later parts of the project. Okay, so let me show you the first and second derivatives of the one period return function. Okay. It's not too difficult to get these functions, but there is a slight possibility of miscalculation. So when you solve this problem at home on paper with pencil, you must be very careful. Trust me, it's very easy to miscalculate, to get lost. Okay, this is the third derivative. Okay, this is also negative.
comma. This is also negative. And of course, this second derivative is the same, so it's not too surprising. It's an opportunity for us to check if the calculations are correct, and they are. So on this basis, we could calculate the determinant of the Hessian, and on this ground we would see that the one period return function is strictly concave. We don't need this result, but we need the partial derivatives. So I promised that we are going to do the linear approximation to the Euler equation, so let's do this. First, we need the Euler equation. General form of the Euler equation is this. I will show you two equivalent forms just to call your attention to a problem source. So these forms are equivalent, but and the book and the solutions guide use both, but please be aware of the possible change of sign. If you disregard this change, this possibility, then everything may be messed up. So you must be very careful so you must be very careful which form you use, and you must use consistently the same form throughout the operations. Okay, to have the Euler equation, we need the first order condition and the envelope condition. The first order condition is very simple. Just a kind reminder, when you have the Bellman equation, you derivate the Bellman equation with respect to the control y, and you receive the first order condition. The envelope condition comes from the optimized value function under the assumption that we actually have the optimum policy function. We don't need to have. We only assume we have the optimum policy function, and we know that when the problem is solved under the standard assumptions, there is such a function. And according to the envelope theorem, we can estimate the effects of any change in the state variable by derivating the value function, the optimized value function with respect to k, the state variable, by neglecting the indirect effects that come through the policy function. So this is the optimized value function with the optimum policy function. And if we derivate this function with respect to k, we receive this equation, which we regard as the envelope condition. It holds for every k, so it holds for y or k prime. So we can write this equation too. Okay. You know, you can see we have k, y, y prime. So we can introduce the time indices because they make things much simpler, trust me. So by having the first order condition and the envelope condition, we put these species into the general form of the Euler equation, and we receive this equation with time indices. So this is a full-fledged, very nice Euler equation, which you can see is a second order nonlinear difference equation. This is a second order nonlinear difference equation. And to be correct, this is the left-hand side and this is the right-hand side, just to be clear and just to be accurate. Okay. The ultimate goal, just as a kind reminder, it's a pointer. We want to make a linear approximation to the Euler equation in the close neighborhood of the steady state. So before doing anything else, we need to find the steady state. In the steady state, this condition holds. So shortly put, in the steady state, we are in the steady state. So we need to solve the Euler equation for the same k. And after some steps, we receive the solution for the steady state capital stock. This is the steady state. Okay, so we have the steady state, and in the close neighborhood of this steady state, we are going to work out the linear approximation to the Euler equation. So let's use this form of the Euler equation. Because in this form, with this form, we don't need to check and check and check time and again the signs. And let me show you what it takes to write a linear approximation using the Taylor polynomials to, this is a sum, so I will show you what it takes to work out a linear approximation to one of the sums, first half of the sum. Let me pick this half of the left-hand side for demonstration. So we have this component on the left-hand side, and to this I want to write a Taylor polynomial in the steady state. I don't want to go into details of Taylor polynomials because it's very effectively summarized in your math reference book I suggested you should use in the first lecture. So if you are uncertain in setting up Taylor polynomials, then please go back to the math book and you will find exactly the same solution to the problem. So this is the linear approximation using the Taylor polynomial to the first half of the left-hand side of the Euler equation. By the same method, we can set up a similar, an equivalent linear approximation to this second part of the left-hand side. So after some manipulation, which is demanding, trust me. So when doing the math underlying this exercise, you must be patient because it is lengthy. So after a few steps, after some work, we receive this equation. Oh, geez, sorry. All right. Z equals 0. So this is the linear approximation to the second order difference equation, the Euler equation. So now we have a second order nonlinear linear difference equation for the difference variable. This is a linear equation which is appropriate but not first order. So we need to squeeze the whole stuff into a first order equation with a very simple trick I will show you in a minute. Let me introduce some simplification. To show you that this is the familiar thing. So after some rearrangement, we have this form. Which is the same as we studied previously. So this is a linear second order, sorry. This is a linear second order, okay, to Aries human. So this is a linear second order difference equation with which it is very easy to work because it can be stacked into a first order form by the basic rules of linear algebra. This is a vector first order difference equation. See, that's all. So this equation now is in a, which is second order. This is now in a first order vector difference equation. That's all. That's all. So from this point, everything can be treated within the boundaries of first order linear difference equations. You may remember that everything depends on the eigenvalues of matrix A. To find the eigenvalues of matrix A, we need to solve the characteristic equation. So what we need to do is to solve this determinant. I mean, what we need is this difference. This is a 2 times 2 matrix. Okay, so this is the matrix we are working with. And to find the eigenvalues, we need the determinant of this matrix. And this determinant is supposed to be 0. This is a simple determinant, the simplest case. And by doing the math, we find that this is the so-called characteristic equation of the matrix. This is a quadratic function in lambda, the eigenvalue. So it is very simple to solve by the usual stuff. This is what we have. And actually we are moving at so general a level that we don't need more. What we need to show is so the best bet to show that one of the eigenvalues is less than 1 is to show that this equality holds. It is not a guarantee, but a nice first step to show that one of the eigenvalues is less than 1. So let's do it, and after solving this part of the problem, there is one more step to take. So let's use the usual formula. Because of the signs, everything is very simple. Okay, and after a few steps, it turns out that lambda 1 times lambda 2 is 1 over beta. So this is a very important first step to show that one of the roots, one of the eigenvalues is less than 1. There is one thing to check. You may remember that local stability requires that at least one of the eigenvalues should be less than 1 in absolute value, in modulus. Sorry. So we need to check the conditions under which it is true that one of the eigenvalues is less than 1. So what do we know about the eigenvalues? Not too much, but you will see it's enough. So we have 2 eigenvalues, and given the fact that B is positive it's a thing that so it is easy to prove that b is positive. So of the two eigenvalues, this is the larger one. This is the larger one. This is the one that lies closer to 0. This is the larger of the two. If we can show that this eigenvalue is less than 1 in absolute value, then the other eigenvalue, lambda 2, can be whatever. So, what we need to show is this eigenvalue is less than 1 in absolute value. Given that this is negative, okay, we know that both of the eigenvalues are negative. Please check exercise 6.6 because the second, because this derivative is negative, both eigenvalues are negative. Let me check in the book for a second. So on page 156, this is exercise 6.6. If fxy is negative, then both eigenvalues are negative. So this is something we should keep in mind. So we know that both of the eigenvalues are negative. So from this inequality, we can easily get to another one. Okay, which means that this is also true. And this is also true. And after a few steps, we get to this inequality. So if this inequality holds, then one of the roots, one of the eigenvalues of the matrix is less than 1, and it follows that the steady state, the stationary point we found, is locally stable. After some steps, we receive this condition. If this condition holds, then one of the eigenvalues is less than 1 in absolute value, and the steady state is locally stable. But please note and please remember, it is one thing to demonstrate that the eigenvalues come in reciprocals, but it's another thing to show that one of them is one of them is lower than 1 in absolute value. So this is the reason why we took two distinct steps. And last but not least, a few thoughts about the global stability of dynamic economic problems. The study of global stability is based on a simple definition and a lemma. The definition of global stability is very simple.
if we have a dynamic optimization problem with a linear or nonlinear policy function, for all the sequences that satisfy the policy equation, as t approaches infinity, xt must approach the steady state. If this condition holds, then we can say that the steady state we found is globally stable. It is easy to say, but it's another problem to demonstrate if a steady state is globally stable. To do so, we need the so-called Lyapunov functions, which is not too easy to find. So the book offers one very generally applicable Lyapunov function. You can see in the slide, you can see the conditions which must hold for a function, and if we have a function to which these conditions hold, then it is globally stable. Then the stationary point is globally stable. The problem in this definition and lemma is to have a function, an appropriate function, Lx function, that can be useful to examine whether a stationary point is stable. So by using the strict concavity of the value function, we can have one, and actually the authors, Stoke and Lucas, use this condition, so we can have a very general Lyapunov function by which we can check if we have a stationary point, then it is globally stable or not. The problem, if you have a look at the Lyapunov functions they offer, the problem is we seem to need to know both the value function and the policy function. Luckily, it's not true. So with some simple algebra, by using the first order condition and the envelope condition, we can get to a form in which the first and second derivative of the one period return function show up. So on this ground, it's easier to check if a stationary point is globally stable or not. Actually, in exercise 6.9, it's a very tough exercise, so I suggest you should do that. You should do the math from line to line. So in exercise 6.9, you can realize that checking global and local stability are interrelated. So in checking global stability, we can use the results from local stability analysis. And if we have a locally stable stationary point, then this stationary point, then the steady state, may be globally stable, and the demonstration is not too complicated because we can use the results from the local stability analysis.